Based on some excellent question by a student in the class, I thought I would do an addendum to lecture 35, just a little bit of a mini lecture with an example to try to provide context. And largely because we've been talking about power, we are coming to sinusoidal power at the end of the semester. I'm always concerned about packing content that late in the semester where students are pretty much getting ready for final exam. What I wanted to do with complex power is to provide you some familiarity with the various power calculations, get you to know what they are, do some minimal interpretation of things like power factor, know if they're leading, lagging, if you're looking at from an impedance point of view, whether you can classify as an inductive and capacitive. A little bit more interpretation understanding really requires more courses in electrical engineering. Many of you won't do that because you are non-electrical engineering majors. So I wanted to somewhat tidy up things a little bit so that those of you who are possibly going on to electrical engineering will have a little bit more context for the power calculation and the various power calculations that we've seen thus far. So let me go to the document camera for a little bit, and then I'll go back and then do one last example as an addendum to lecture 35. Okay, so one thing that I'm going to arc back to essentially just a little bit of a recall that we've covered Thevenin, and you'll know why I'm going from there in Norton model. For one port network, okay, or circuit. And when we do that, essentially, we look at, in essence, the Thevenin impedance. If we're looking at a Thevenin with a VOC, okay, we can model a one port, two terminals using the Thevenin model, essentially an ideal voltage source in series with the Thevenin impedance, or we can do it using a Norton model with the same Thevenin impedance, but a current source model. Okay, so these are the Thevenin and Norton model that we've seen there. And of course, we can look at the Thevenin impedance, we can model it as a resistance plus a reactance. Okay, that's pretty common. That is to do that, to model the Thevenin impedance for that. The reason I'm bringing that up, it's because you also should see that both of those practical source models. Okay, so this is a practical voltage source model, and this is a practical current source model. In fact, when we cannot calculate the Thevenin impedance because we cannot combine resistance, we often do that by using the practical source model. If we calculate VOC and we calculate ISC, we do that. So where I'm going with this, it's the concept of power. So if we, for example, look at the Thevenin model and we look at it as a source model, so we can look at it and we'll call this VS to refer to a source. And this would be, I'm making it a general complex resistance here. This would be a typical accurate model for a source, an ideal voltage source VS in series with the source impedance. Okay, and then now, of course, we would connect this to a particular circuit, some kind of load, and then we can talk about how do we send maximum power to that load. I've avoided doing the maximum power discussion for sinusoidal circuit because it's so late into the semester. I feel like I'm packing content, but this is a context. This is a content that we can, and if that load is some RL plus JXL, we can actually design the load in relation to the source resistance and the source reactance, the source impedance, if you will, so that the load gets maximum power. So there are the discussion that we could have. Okay, what happens if we cannot change RL, but we can only change XL? So what would that do? And what happens if we can change both? So there are various scenarios about sending maximum average power to a load that we could model as an impedance RL plus JXL. Okay, so I'm going to do an example, but clearly, if this particular load, for example, is a capacitor, we've talked about the average power for a capacitor is 0, similarly for an inductor. Okay, so the concept of power becomes important. So arcing back, I'm going to show you an example, and then you'll see a little bit more context of where I'm going with this. So what this example is talking about here is an example where you have just give me a second here. You have a particular source model here, a practical source model, which is given by the voltage Vs in series by a source resistance, 50 ohm. That actually is a pretty good model for a real source. And it connects to a particular circuit that's given by what's in the box here. Okay, so that's the circuit model. You could be some neighborhood on some circuit here. And what this problem again is a little bit beyond where you are in this course, but I wanted to show you this as to give you a little bit of a practical context application for this kind of power consideration here. And what this problem is saying, essentially, the utility company wants to come in and across the load here, which we putting in that box here, it want to add some capacitive or inductive element, a reactive element, such that the power factor that the source see, it's 1. Because you now know that if the power factor is 0, if the power factor essentially could be 0, then you're sending no power to that load, which you wouldn't want to do. So the power factor being 1 is a way to essentially send a certain amount of good amount of power to a load. So this particular problem somewhat is giving you that hint. There are many ways we can frame the maximum power discussion, but in this particular case, it's saying, okay, we're going to add a reactive element across a particular load given by this circuit here. And we want to design that reactive element. We want to design it such that it produces a unit power factor. And this whole discussion comes back because if you have a power factor that's 90, if you have a power factor if you have a capacitive or inductive element, you're going to have a power factor that's 0. So that's going to give you a 0 average power. So you're sending no power. So clearly the power factor being 1 is sending more power than if you had a power factor that's being 0. So we're going to design this here. And I'm going to show you that here, how we do this. So specifically here, the 377 is a 60 hertz. The radial frequency for 60 hertz is 2 times pi times 60. So I'm kind of bringing a problem that's a little bit more practical to the power industry, if you will. And then, of course, this in the box here model some load that we have, and we're trying to find that reactive element Z here. So I'm going to pretty soon call it JX, X being an unknown, and so that the source sees a power factor of 1. Okay. So how are we going to do this here? So basically from here, I'm going to convert this circuit to phasor. All right. Essentially calculating the impedance for the inductors and capacitors, if you will, and for the source. Okay. And you can see me putting JX, where X will be an unknown. X is what I'm designing this thing so that we have a power factor of 1. And the idea essentially, I want to design this. I want to calculate the value X that gives me basically an input impedance here, an impedance looking in with JX that is a real number. If the impedance looking in is a real number, then obviously the current will be essentially in phase with the voltage. So I will have a power factor of 1. So I'm going to calculate, I'm just going to combine impedances and calculate the impedance Z in, looking in toward JX. And then at some point, I'm going to set the imaginary part of the impedance to 0 and calculate X, that gives me that. Just give you a little bit of a flavor for a design example, something that's frankly a little bit beyond you where you are, but I'm hoping it gives you context in terms of understanding the applications. So I'm going to start by combining things. So these two elements are in parallel, so I'll combine their impedances. And when I do, I get this, okay? Typical parallel combination between the 60 ohm and the minus J26.5 from the capacitor. Okay, and then after that, I'm going to combine the impedance of the inductor in series with that. So these two are in series, so I simply add them, so I get this. Okay, all right. And of course, right now, actually, I could just combine all three on the right in parallel, but I'm going to first combine with a 100 ohm. So I combine with a 100 ohm in parallel with the 9.8 minus J14.6. And that gives me this. And then the final step is to combine these two in parallel. Okay, I'm going to combine these two in parallel, and then you get the math. So you get JX times this impedance plus JX plus that. All right. So what I'm doing after that, to go from here to here, I multiply the top and bottom of my equation by the conjugate of the denominator. And when I multiply the denominator by its conjugate, I'm going to get a real number, which is right here, which is the magnitude of that complex number at the bottom. Okay, because I want everything to be in the numerator, because eventually I'm going to set the numerator to be, I'm going to set the imaginary part of the numerator to be 0 and calculate the X that gives me this. So that's what I do here. I multiply the top and bottom. So you can see that I'm basically using the conjugate because I change the sign of the JX. So you have JX on the left, and then I have minus JX. And I also change the sign. I have minus J11.9 on the right, and I put it as plus. So you change the sign of the J, that gives you the complex conjugate here. And then when I multiply, I get, let me just clean up a little bit here. I get this final complex number for the impedance looking in. Okay, so now I'm going to say I want the imaginary part to be 0. That's going to give me a real impedance looking in. Thus, the power factor would be 1. Okay, I can accomplish that in two ways. The one easy way you can see that I accomplish that is if I make X equals 0. Does that help me? If I make X equals 0, then I'm shorting the circuit. X equals 0 essentially is a short. That's what it would be. So clearly that would also make the power factor 1, but it wouldn't be useful because essentially I'm shorting the load on my right. So that would be a bad option. The better option is to make what's in the brackets here to be 0. And I can solve for X such that what's in the bracket here is 0. That will force the imaginary part to be 0. That will give me a real input, a real impedance looking in. And if I do that, again, the imaginary part of Z in is 0, I can basically solve, and that gives me an X equal 21.2. Okay, so this will be an inductor given the frequency, the radial frequency of 377. I can calculate the inductance that would give me such an impedance. That would be a 56.25 millihenry inductor. Okay. If I add that across, I'm going to have an impedance that's real. All right. So I just wanted to show you that, and that's going to give me a power factor that's 1 because the current is going to be in phase with the voltage. So I thought this problem will give you a little bit of a contextual understanding application, even though frankly I wouldn't ask you something that complicated. It's a little bit beyond, but those of you who continue to in electrical engineering, I think that hopefully that will be helpful in getting that application. So if we include the inductor here, that inductor I calculate here, and then we can calculate the current, and you can see that by simply, so the input impedance Z in then become 24.05, and I can simply calculate the current by dividing the voltage by the sum of the impedance, and I get the current. So you can see that the current and the voltage are in phase; they have the same phase. So the power factor is going to be 1. So hopefully that's helpful.